All right, so for those that are only seeing the recording, you missed the intro. That's the prize for being here. Very well. Any other questions before I jump into that? All right. I lost where I was. Sorry. My own fault here. What was I saying about getting things right? There we go. All right. So I think there are effectively two types of network data visualization that you want to keep in mind. The first is just exploratory analysis, right? And this is just your thing that you do as you're playing with the network, and you're trying to learn your data to make sure that the network looks right. And so for getting there, it's useful to, your graphs don't have to be perfect. They don't have to be, labeled and everything else, and your sizing and coloring can be whatever the defaults are. But it is useful to know what it is you're looking at. And so I find essentially that it's useful for me when I do data visualization for exploratory purposes to do a couple of things often, which is that I usually color by different things on the same layout whenever I can, just to make sure that I'm seeing what I expect to see. And then I also do a lot of work to make sure that I try different versions of the same family of layouts to make sure there's not anything that's odd. Now, I've said 2 or 3 times now, nothing's odd or nothing's out of work or check things. What am I looking for? When I'm doing network visualizations, I'm often looking for the kinds of patterns that should be impossible in my data or incredibly unlikely. So if I'm dealing with adolescents in high school, which I often am, which is a different story entirely, but if that's the case, right, then it ought to be the case that there's clumpiness in the network that's related to the grade in school. So if I'm, in this case, you can see that you have 7th and 8th graders over here in the top, you have the high school down at the bottom. Within the high school, you see the seniors in yellow, you have the freshmen in blue, the freshmen are closer to the junior high than they are to the seniors. Like, that's all makes sense. If I had a high school network and I plotted it and these colors were randomly distributed around the network, something's wrong. I probably have a sort error somewhere. Similarly, in most American high schools, if there's about half of them are black and half of them are white in a single school, it's highly likely that it's a racially segregated setting. So if I found race was randomly distributed around this school, that would be a signal to me that something I definitely want to look and check. It'd be great news, but it seems highly unlikely in most American settings. I want to figure out why, if that's the case. And so that's the kind of thing you want to look at. And so the first one you're looking at these kind of exploratory features is just those kinds of associations. Like, are the people near each other that you would expect to be near each other in the graph? And the other I tend to look for is really high crazy degree. So another sort of standard error that you'll see in a visualization that just pops out immediately is there'll be like one node in the middle that has, 90% of the nodes are tied to it. Now, that's not real, right? There's nothing in your data that made that true. You probably had a missing value code that got coded as a real ID. And then it turns out that node 999 is the most popular node in your network because everybody nominated a random node. And so you should have caught that when you were cleaning the data initially, but you didn't. And so there it is, right in front of you. So you can see that, it's there, you grab it, you fix it. And those kinds of processes are iterative. And it's nice to be able to do things like turn on the loops and to look at reciprocity and to turn things on and off when you visualize in order to check for those kinds of data mistakes and errors. It just really makes it easier to see. So I spent a lot of time doing that kind of work. Now, one of the things about visualization that I'm always trying to impress on people is that there is no, there are lots of wrong visualizations, there are lots of bad visualizations, but there's no correct visualization, right? So all of these images are of the exact same underlying data. So these are different projections of literally the same network. And so it turns out in this network, it's a directed acyclic graph with a root. And so this is probably the most intuitive way to look at it. These two are not intuitive. There's nothing about the spatial orientation that helps you learn something about the structure. But at minimum, like there's nothing technically wrong with this. Like there's no, and it's not inaccurate. If by accuracy you mean I can go from the image back to the data file, you could, in this case, if you were bored enough, you could label them and write down the words, and it would be an accurate representation. It's just not an informative representation. So what I mean by that is that on the one hand, that does a couple of things for us, right? It highlights the fact that there are different ways to visualize things, and so you should do it. But the main thing that it highlights is that there is a clear distinction between accuracy and informativeness, and you shouldn't let one trump the other. And so there are times, particularly in exploratory analysis, when it's useful for you to get in there and move things around by hand and sort through things and do things that you would never do to a scatter plot. And that's because this isn't a scatter plot. And you might think of it like a scatter plot, but you shouldn't. You should think of it as a tool for helping to communicate a high dimensional data object. And that tool is best done with your help. And so a little bit of guidance can go a long way. So there's a lot of bad visualizations, right? So these are 3 visualizations of the exact same data. Just to show you in practice, like this does happen, right? So these are the Zachary Karate Club and 3 different published works. I don't know why you would ever use a circular layout like this. I know why. I've written with both White and Harari. I know why they did this. It doesn't make it a better visualization. And this one is probably the best, right? So there's a reason they do it. And I think that when you see bad visualizations, you have to ask yourself, well, what makes me react badly to it? And I think it has to do with this little triangle, right? Which there is a synergy problem between the visualization strategy you have, the accuracy, and the knowledge problem you're trying to solve. So ideally, what you're trying to do is align these 3 things so that they're all working together. And if that happens, then you can then you win. If it doesn't happen, you need to go back and do it again until you do. In order to get there, it's useful to understand a little bit about what the basic network visualization rubrics are. And so there are 3 basic ways to do layouts. The first one I refer to as a tree-based layout, or a vertical or an axis-oriented layout. And so in this case, one of the dimensions is meaningful in the same way a scatter plot is. So there's a difference between nodes that are high on the axis and nodes that are low on the axis. And the classic example here is something like an organizational chart. So you have the boss at the top, you have the vice president, below that person, and then you have the hourly employees at the very bottom. And that's a classic sort of organizational chart. So you have your provost, you have your vice presidents, and all the way down to graduate students at the bottom. So this is the people paid by Duke. That was what the organizational tree looks like. I've actually asked Duke for an organizational tree every year that I've been here, and they won't give me one because I would love to plot it. I think they're afraid to see it in the newspaper. But we have way too many people at the top of this tree at Duke, if you ask me. So anyway, so one version is a hierarchy. It's a tree-based layout, and it works best when there is something that matches on the underlying social process to that kind of a thing. So authority flows from top down. And so if you have authority relations on the network, it works well to array them this way. A force-based or a space-based layout is a layout where you don't care what's up or what's down. All you care about is proximity. And so 2 nodes are close to each other if they share a tie, and they're far apart if they don't share a tie. Now, the thing about networks is that they are multidimensional objects that you're forcing into 2 dimensions. And so in this case, if you're say that our 2 nodes that are tied to each other should be only distance 1 apart, you can see that node A here and node B are 1 apart, they're 1 apart, and they're 1 apart. But what you would expect is that A and C here are also 1 apart, but they can't be, right? So it's impossible to make all 4 of these nodes equidistant apart if they're all tied, right? So this ability to make these things perfectly transitive in a fit sense doesn't work well. Now it does in the line, but as soon as you get a branch, then you have to create a difference in distance. And so there's always going to be a bit of a misfit between the distance based layout and the graph layout, but the goal is to minimize the errors that happen there. You want to make that as intuitively possible. The force-based layouts are best suited to the kinds of problems where social proximity is the question. So if you have a network where you're trying to identify what's driving clumpiness or closed cycles in the network, then a space-based layout is best because you can see the little knots of nodes that are tightly connected to each other. They pop out because they're all close to each other. So if social proximity is driving the relationship structure, then a physical proximity on the screen is usually a pretty good approximation of that, or at least one of the better ways to approximate it. You can turn this kind of a network into a axis-oriented layout, a tree-based layout. It's useless. It doesn't tell you any more information, but it's possible, right? So it's lots of ways to get a bad network. So that's one way to do it. So those are the two basics. The third basic way of laying things out is to use some kind of fixed coordinate. And that is, there's some other bit of information that defines the layout space that your readers already know, and thus you're going to take advantage of it. The obvious case here is a map, right? So these are hospitals that share patients, and so this is the patient sharing network, and they're spread out in what's actually a pretty poor version of a latitude and longitude, because I didn't actually fit it on the sphere. I projected it on X and Y. And so, but you can see, right, that this is, it's obvious what this is. I know that that's Florida, I know that that's Washington, I know that the Northeast is up here, and there's a bunch of things around Chicago, right? So it's pretty easy to see what that is. I could use a space-based layout, which is what you're seeing over here on the right. It's the exact same network in a different layout. And in fact, it fits better. I'm going to describe what this fit is in a second. But it's not as intuitive, right? So if you look at this node in the network, what fit is the correlation between the distance on the screen and the distance in the graph space. So if you think of the number of hops it takes to get from node to node, that defines the graph distance. Well, if the space-based layout is working really well, those two should be highly correlated. And we can see here that this network fits on that metric better than this one, but I suspect that most of us would find the map of the United States more intuitive. Maps don't fit because of classic geographic distortion. There's a big mountain range right here and a bunch of farms right here that make it impossible for hospitals to be there, and thus you don't get a lot of people connected to each other. Whereas over here, there's lots of hospitals going on, and so you get a much more tight set. So that's what's occurring. There are other kinds of fixed layout systems. The most obvious one is a circle graph, right? So you just take a network and you put everything on the circle, like we saw in the Karate Club above. That's that wasn't in the bad old days, in the real back, even too early for me bad old days. This was a common way to make network visualizations because people were doing them by hand, like literally drawing the image that they're going to put in the publication with their pencil and a paper from a sheet. And the advantage of doing it in a circle is that you never have occlusion. You never have two edges exactly on top of each other, because there's always some element of a chord between them. And so you can use a ruler and you can put it on there and you can be accurate doing it by hand in ways that are really hard to do freestyle. I don't find circles graphs particularly useful most of the time, with the one exception of combining a space-based layout with a circle-based layout. And so this is this graph where I've taken that space. You can see this little black set up here is this black set here. And I've just put them in the same spot, but I've taken each cluster of this community and just made those a circle. And so what this does for you is highlight the internal density of communities while giving you some sense of how communities are related to each other. There are times when that can be a useful sort of way to do space-based layouts, to do fixed coordinate layouts. But most of the time, fixed coordinate layouts are pretty useless, which is weird because this is one of the most popular graph styles out there right now. It's called a chord diagram. And I, for the life of me, can't figure out why people like these. They're just a very colorful circle layout of a network, and almost always you'd be better off doing a space-based layout. But they are pretty, and so I think that's why they're popular. All right, so then if we've taken to this notion that a space-based layout matters, is there a time when we would like to somehow otherwise distort the space to help tell the story? And I think that that's the big picture of today, is that sometimes the answer is yes. So if we let the algorithm find the optimal fit for the two-dimensional representation of this network, it's the version on the left. What you see is that there's a fair amount of overlap between the green group and the red group and the yellow group and the orange group. And it might be nice to, especially if my story is about differences between groups, to highlight that. And so what I've done is I've weighted in-group ties a little heavier than between-group ties and ran it again. And what that does is it creates a separation between the clusters. Now, you should report that you did that in your report, but it does make it clear that these two communities are different from each other. Now, you might say that what it's doing is it's unfairly distorting the network, right? Because it might be that these pink nodes should be in green or in red, and you can see that better here, that it's sort of reifying a bad community detection. That could be true, and so that's one of the judgments that you need to make as an analyst, whether or not that's a useful thing to do or not. The other thing that's often useful is to spread out nodes a little bit that are otherwise too overlapping. So the thing about a really good space-based fit is that it'll take structurally equivalent nodes with the exact same patterns of ties, and literally put them in the exact same place in the network. And so you can't see who's there. So one solution to this is to use transparency, like if you're doing it. The other solution is to use what's called a fisheye lens. And so you can do local fisheye distortions where you go into each of these really dense areas and you spread those out. And that it takes a space that should be a grid and it creates it a little magnifying glass over those spots. And that's what I've done here and here. And I've sacrificed, a tiny little bit of fit, but it tells you that there's a lot more going on in this cluster than you would have seen otherwise. Now, you might like the other one better, but that's for the purpose of figuring out what's going on. That's one way it's there. If you've ever used Gephi, its default is to have a curved edge. As a general rule, I don't really like it. It provides too much. It is adding more ink to the page. But I've softened my position on this a little bit. In particular, it's for larger networks, it's a lot easier to see reciprocity when you have arcs that double up, sort of complementary each other, as opposed to trying to see whether or not there's an arrowhead or something on it. So there are times that it can be useful, but just be aware that use it sparingly. There are a lot of times when you're doing a network visualization when you don't really need to see a network. And this is where I say it's really nice to have some level of abstraction. In a Senate co-voting network, for example, if I vote with you and you vote with me and we all vote together, it creates these big cliques. And so these big cliques are kind of uninformative. It's just a big mess. And so one solution to that is to abstract away from the point and lines and to instead look at the heat matrix. And so you can take your adjacency matrix, you can pixelize it, and you can say, some kind of a dark shade indicating a tie and kind of a light shade indicating an odd tie, and you can see immediately which of these nodes are crossing the aisle, right? So these 3 nodes here, 4, maybe 5, are nodes that are somehow working together across the aisles where the others are not. And so that pops out immediately in the adjacency matrix in a way that doesn't. Now, this requires you to sort the adjacency matrix in some meaningful way. And so in this case, it's sorted Democrats and Republicans. If you didn't do that, you would not have it. You might also find in many cases that it's good to abstract away from the network entirely and instead plot a process on the network. So in this case, what we've done is we've plotted this is what Katz, Coleman, and Menzel plotted with the adoption of an innovation, but they just ordered it by high degree nodes, middle degree nodes, and low degree nodes. And so there's a network dynamic generating a diffusion curve, and sometimes the diffusion curve is easier to see. You could simulate a diffusion curve on a network and see what the entire universe of diffusion potentials are on a given space. And this plot would look different than a sociogram, certainly, but it would tell you that the bulk of diffusion, wherever you start, is going to happen within like 3 or 4 steps. And there's this long tail of nodes that if you happen to start your infection with them, it's going to take a long time for that diffusion process to happen. So this might be a nice way to communicate the difference between one setting and another if you wanted to look at it. Excuse me. If you actually have a diffusion tree, it's nice to plot it. So this is what a sexual network simulation looks like on a pseudo commercial sex worker graph. This is work with Giovanna Merli and data she's collected in Shanghai. And what we were able to do there was show that the concurrency in the graph really had an effect on getting these really long chains. And it's a little hard to see when you just look at whether or not each edge is concurrent or not, red or blue. But if instead you ask, is there any concurrency upstream of me? You can see that like the thing that distinguishes this one is that everybody has some concurrency upstream of them, and you don't get any of these long chains unless you have some. So concurrency ends up being a necessary but not sufficient feature for getting these long chains in the network. There's a lot of interest these days in dynamic networks, and one solution to dynamic networks is to animate them. And so we, myself and Dan McFarland and Sky Vindermal have done a fair amount of work on this. It's a nice way to see things. It's kind of cute. The problem with dynamic animations is that your vision has a hard time seeing them. So it's nice to have, in this case, you can flip back and forth and see how the network evolves. It goes from being relatively sparse to growing over the time. It can't not grow. These are current versus past relations. So I'm just accumulating the waves over time. Another way to do that, Sky has this really nice way of layering panels of networks over time. So that you could do that. This is the same idea done to the Prosper network. But in general, what you need to do is find some way to layer on the information that you think is useful. What I've done here is I've taken a default network, which is just fine for my own exploratory purposes, and I've added to it. Why did that stop? There we go. I've added to it different kinds of information, either by sizing the nodes or by coloring the nodes to help highlight what's there. And I think that this is a better vision. The after is better than the before. And it just takes a little bit of care in terms of picking your colors and things like this. Now, there's a whole thing we can do on colors and size and line weights and things like this. But I tend to think that anything you can do to help make an image crisp and clean with reinforced elements. So in this case, degree, closeness, centrality, and color all reinforce the same amount of information about whether you're at the middle of this ring or the outside of it. This is another example. The before in this case is a network that Jacob Moreno put together by hand. One of the things from Who Shall Survive is one of the first network images out there. And again, that he just did it literally intuitively by hand. And if you spend a little time playing with this network, you realize that the real story in this network is that this node, CM, is everyone hates her, like for whatever reason, like it's all antagonism going into CM, and CM's one close friend is not friends with anybody else, right? So you end up like that becomes the central story. And then once you unpack what's there by hand, you realize there are subgroups. And so we redid this image in a way that tries to highlight some of those other stories that are present inside the network. And I think it's a nice way to recognize that you can do some things with these features, and you'll learn more about the setting. We tried as best we could to keep the hand-drawn labeling just for historical purposes, because we thought it was kind of cute. That's just the kind of thing for fun. So this is just a quick overview. Again, there's a lot more detail in the other presentation about how you use some of these things, but I think I'll stop there and try to answer any questions that people might have about good practice and bad practice, or hear war stories as people might have them. So. Any reactions or thoughts? Everyone, please, Margaret.
Well, I was just thinking about how I've often, when I work with not huge networks, but perhaps a little bit larger networks, I find it really difficult to make anything meaningful using iGraph or gggraph. And so like it sometimes just doesn't work particularly well. So I was wondering if anyone has any, like, what are your tricks for working with larger networks? Do you have particular packages that you turn to? Do you leave R entirely? Like, what do folks do?
I leave R entirely.
Okay.
I use Payek almost exclusively, particularly when I'm trying to do anything large. And there are two things that I like about. I think you could do the same thing with Gephi. You could use YED. I'm not saying you couldn't do that in those packages, but the features that I like about Payek are the ability to color. I'm like pretty easy, and to grab by colors and sort. So you can literally pull, you can click next to a color and pull all of that color off to the side. So if you want to essentially sort the network by race and see what that does, or sort it by gender or what have you, it ends up being pretty easy to do that way. It also has the ability, like one of my favorite layout algorithms is the Fruchterman-Reingold algorithm. The most frustrating thing about iGraph's implementation of Fruchterman-Reingold is it doesn't let you adjust the temperature. Under the hood of Fruchterman-Reingold is a temperature dial that tells you how much you're trying to push versus how much you pull together. And in Payek, that's easy to do. And a lot of times when you see a Fruchterman-Reingold network that looks like a big circle or looks like a knot, it's because that knob hasn't been turned right.
Okay, that's helpful. Thank you. I will learn more software.
What about someone else must have other ones there? Yeah, that's Gabe. Explain what that means.
I mean, so yeah, the alternative. Well, one alternative is also to if you have some like reasonable way to pull the backbone of the network. So select edges that you think are like most important in some way, like whether it's because of some like weight. It's like the most repeated ones, or there's all kinds of ways of pulling the backbone. But if you can select in some reasonable way what are the most important edges and then just plot those, then you can tell a story of like what is fundamentally about the network while removing most of the nodes that like are just piling on to the same fundamental core structure. And that happens a lot with word networks. So if you're plotting semantic networks, a lot of the time, most of the information you have in your graph is completely useless. Every semantic network is essentially a hairball by default. And then it's just a question of saying like, what's the backbone of it? But then the question is like, how do you define what the backbone is? I think it falls into what Jim was talking about, which is the analyst's decision-making and reporting. Yeah.
That's also helpful. Thank you.
Anyone else? Thoughts or questions?
Two thoughts. One of them is I just put in a link that is a set of tools that allows you to go back and forth between R and Payek. So if you're doing data manipulation or most in your statistical analyses in R and you want to move things. So it's linked to the Payek site. If I built those tools, so you have questions about them, I can help you with them. The other thing is there's another network visualization that's nice for very large networks, which is to basically create a topographic representation. So if you can get the X, Y coordinates, even if your network looks totally junky, and then get a kernel density of that network, you can create a really nice topographic network. And you can do that. It's relatively easy to do that kind of visualization with ggplot too. I don't always recommend it, ggplot, but in this case, that's a nice way to do that. There's Jim has examples of like what I'm talking about, but it looks like a topographic map. So imagine a contour map, except now the lines indicate the density or the concentration of the nodes in certain parts of space. And then what you can do is you go, okay, you get that. If you know roughly where the partitions are, you can put labels to sort of indicate, okay, there's a peak here, and that's this community, and that's these kinds of users. So one nice example that we did several years ago was looking at science knowledge disciplines and how they interact with each other. And so you could see co-citation networks where you have different fields. So that's an alternative on a really large graph where yes, nodes and edges don't really work. And the other thing, and I think Jim's already hit on this quite a bit, but you can move to 2D representations of key things that you want. So like for instance, if it depends on what the sort of story you're talking about, but like if the story is, hey, this is a core periphery network and there's lots of core concentration in the core, not a lot out in the periphery, you could visualize that by just a degree distribution where there's very long tail, and most of the stuff is hovering around 0, 1, and you just have like a little comment that sort of explains that relationship, as opposed to trying to show that via a graph. So there's multiple ways to sort of work that problem.
Alison, you had a question?
Yeah, I'm just wondering about the visualization. Like you do that after your analysis when you figure out your main, like when you're saying you can distort things, like do it by degree, like enlarge certain bubbles, but in your analysis, you should be showing that degree matters, right? Like your visualization should follow your main findings, because you could find no differences, and then, but the image looks like.
Yeah, no, I think I tend to think of it as more of a conversation process. So I often, almost without fail, the first thing I will do is a quick plot of the network, just to, again, as part of the data cleaning and checking process. And then you go into your story and figuring out what the analysis is, and then moving back and forth. So I consider it largely a process of moving back and forth. Now, a lot of that back and forth process, those are ugly graphs, right? They are not graphs that I would share with anyone, but they're teaching me what's going on in my data. And then once I've done that, then you might do something like, think that you've shown that sex matters for smoking, and then you plot it and realize that there's just no association between gender and the sociogram. You got to help yourself make sense of it. And so partially it's to help just do a reality check. But as a general rule, I think you are right that the two should inform each other. It should be the case. If you're finding something only in a visualization that isn't also coming up in your modeling, or vice versa, then you should be at least suspicious of them and convince yourself that it's true. If people haven't seen it before, this is what PAYAC looks like. So this is just an analysis. That's what I mean. Is you can just click and drag things around. You can click next to something and drag it around. And that's a nice feature, especially when, like in these cases, the colors look about the same, but I can tell that there are different clusters on it. So it's a fairly nice thing. It's not the most intuitive program to learn how to use if you've never used it before, but because each element of the data are separate. So you have a network object, you have a partition, you have a sizing, and each of those things are literally independent, and so they're only matched by the fact that they're the same size. And so you got to be careful with things like that. But once you learn its weirdnesses, it can be useful for these things.
And a small plug for NetWrite.
That's right. There's also there are a couple of good programs in R for interactive data. I mean, to his credit, Carter Butts did a remarkable job in the StatNet visualization to allow you to move nodes on smaller networks. But that's there are some better ones now that allow you to do a drag around kind of thing. And I find that, particularly for medium-sized networks, to be quite useful, just to help you learn the setting. All right, folks, thanks for sticking out for the day. You're the few and the strong. We'll see you all, or so hopefully I'll see some of you tomorrow if you're interested in coming back, and there'll be some other people who aren't here yet. If you haven't had a chance to review some of the presentations for tomorrow, please do so. I think it would be nice, and I'm sure the speakers would appreciate having questions asked and such. So that's the plan. All right, folks, thanks so much. We'll see you all tomorrow.
Thank you all.